Numerical optimization of turboelectric distributed propulsion system in hybrid wing body. Abstract. NASA N3X hybrid wing body aircraft has analyzed for optimization of turboelectric distributed propulsion system mounted over aft portion of the fuselage. Here the aircraft configuration has increased strength and reduced weight. The CATIA model of N3X has designed with 8, 12, and 16 propeller over the fuselage. The 3D meshing of aircraft meshed in hypermesh and simulation of different propeller configuration of N3X is analyzed in CFD-Fluent software. The turboelectric distributed propellers are evaluated with rotating wall boundary condition. Keywords: propellers, thrust, turbulence, pressure, velocity. Introduction. The hybrid wing body, also known as blended wing body, is a fixed-wing aircraft concept with zero clear separating line between the wing and main body of the aircraft. The wing and body structures of the aircraft are effortlessly blended together. These kinds of aircrafts have no distinct fuselage. This design aircraft may or may not be tailless. The main advantage of the aircraft is to produce greater lift and to reduce drag. It may be a wide airfoil-shaped body allowing the aircraft to produce greater lift, which reduces size and drag of the wing. The concept of HWB was initially developed and proposed by NASA in the early 1920s. Studies shows that it could carry passengers of about 450 to 800. The HWB also have an advantage of less weight, less noise, and emissions. 2PA rain trick modeling. Several steps were done for modeling and meshing of a hybrid wing body. In first step, the designing of model with certain parameters are done. Fig 1 shows the HWB is designed with different number of propellers, 8, 12 and 16, placing on aft position of the aircraft fuselage with a noise shield covering in it. The propeller is designed with 3 rotating shafts with a connector and base. TE second step includes meshing of aircraft by tetrahedral meshing methods with necessary element sizes as shown in Fig covering in it. TE. Propeller is designed with T3R rotating shafts W with a CO connector and DBASE. TE second step includes meshing of aircraft by tetrahedral meshing methods with necessary element sizes as shown in Fig. 3 flow visualization of HWB and meshing processes. The flow domain over the hybrid wing body W with propeller is taken in such a way so that the stream of air flows freely around the nook and corner of the propeller. The figure shows the streamline flow of velocity of hybrid wing body with propeller. The F figure clearly shows when flow arising from inlet reaches the propeller interact the flow coming from the rotating propeller, thus making the flow diverted around the propeller. From the figure in the table, it can be seen that thrust for HWB with 8, 12 and 16 propeller at 0.74 Mach number R increases gradually when number of propeller increases. We can conclude that thrust continuously increases when number of propeller increases. 7. Conclusion. Thrust is the necessary force which moves an aircraft through the air. The greater thrust and lesser turbulence will give a better aircraft performance. From the analysis, we observed that the hybrid wing body with 16 propellers produces greater thrust when compared to hybrid wing body with 8 and 12 propellers. From the table, we can conclude that the amount of thrust improvement is almost similar at 0.74, 0.84, and 0.94 Mach number. Therefore, by choosing hybrid wing body with 16 propellers at 0.74 Mach number, we can get a better aircraft configuration. This is because of greater thrust production improvement up to 21.58% and lesser turbulence when compared with other 2 Mach number. Hence the HWB with 16 propellers at 0.74 Mach number can produce greater thrust to overcome drag, and lesser turbulence will provide better safety for an aircraft from damage.